Right, let's do another one. So, next problem that we're going to do is this one. Number 102, binary tree level order traversal. Given the root of a binary tree, return the level order traversal of its node values, i.e. from left to right, level by level. Sounds like BFS, but on a tree instead of, well, a graph, but a tree is a graph, it's just acyclic, sometimes directed. I forgot if a criteria tree is that it's if it's directed. Interesting. And anyways, that's a topic for later. So BFS on a tree, and a reminder for myself, but also maybe for some of you. This is actually something that came straight out of cracking the coding interview. BFS is not a recursive function like DFS. You use a queue. So we're going to actually end up taking that approach to this. And luckily for me, and this is actually twice in a row now, first with threesome and now with binary tree level order traversal. These are both questions that I've done before, so I'm a lot more familiar with it. But yeah, level order traversal, it makes sense that if you think of a tree as a graph, then BFS is a pretty natural solution. So the approach that we're going to take, broken down, is that we're going to start at the root. For each layer, create a new list. Or you could call it a queue, right? It doesn't really matter in the context of Kotlin because, well, if you want to use native Kotlin, then you just use a list and you just pull from the front. That's just how it is. You could also use the deck from Java if you really wanted to, but I'm just going to stick with Kotlin for now. So for each layer, you create a new list or queue. Then for the current list that you have, go from left to right, so it's standard linear scan, and add children in the order in which they appear. So basically you just go through the list, you add the left child and the right child, then the next node's left child, right child, and so on and so forth. And then once you're done, create or add the list to the queue of list. And that's pretty much what you do. And that's for printing them out. Let's see. I guess what you could do is that we could create a new list first. Yeah, because I'm basically starting to work on the coding, but before I get ahead of myself, let's also talk about runtime. In this case, you just go through here, here, here. Really, there is an element of sort of checking all the nodes for their children. So I guess to a certain extent, you could say that this is what the height is log n, the width is n. Oh, it's been a while since I've done this. It's been a while since I've done this actually. If you say that if n is the number of nodes in the tree, then arguably O of n, because you just go through all the nodes in the tree. But there is an element of the height of the tree So that's maybe something that to consider. Man, the more that I'm doing this, the more I realize that I really need to practice my big O notation, sort of practice on this. Um, yeah, this is kind of embarrassing actually, for a problem that I've done before. In any case, while I think about this some more in the back of my head, I'm gonna start coding this. So we could say list of lists is mutable list of int. Realistically, we want the. This is weird actually. They want a list of ints, but really we have nodes that we want to traverse. We could call this the return list. And we can create our own traversal list that will start with the root. Of course, if root is null, then we just return a list of there's an empty list of list ints, right? We could just do list of list int, right? Just an empty list. So we know that there's at least one item in here. Also, why is this like that? We could say while traversal list, and we can create a list of root in here. And we can say while traversal list is not empty, we can say the front is going to be equal to traversal list dot first, and we can say traversal list dot remove at 0. So just remove the first item in the queue. I wonder if we can actually just use this traversal list once we're done with it to add into a list. We can think about that in a little bit. Traversal or front dot for each node, and we're gonna need to create a next layer list is a mutable list of TreeNode. We can say if node.left is not null, then next layer list dot add node left. If node.right is not null, next layer list dot add node right. Okay, so then we have that. So now we still have this front list. What if we do val return layer is equal to front dot map. We want to map each element, so let's go back to the collections documentation. No, I did not want that. We can just say list, or mutable list, right? Get this mutable list, and then I want this map function. And basically what this map function, what I want it to do is essentially just turn these values into a list. Okay, so this actually returns it. Awesome, awesome, awesome. So what we do then is not that. not the previous problem, is we would do return list dot add. We will add our front dot map, and this map will map our values, so node into node dot val, and this should return a list of val which is of type int, and that should add it to the return list. So we don't actually even need to add our initial root node into there. We just need to add it here once it's empty and we have no other children. And I think this is kind of the beauty of a functional language like Kotlin here, at least the functional parts of it, right? So let's see if we've missed anything. So if we don't have a root, then we just return an empty list. We will create our return list regardless. And our traversal list, we start off with our root in here. We grab that, and then for each layer we have a new, for each layer we create a next layer. And then for each element within that layer, we will first add their left child, then their right child, right? Into the next layer list. And then at the end, we will add that layer into our front here, into our return list. And then at the end, we can just return our return list. Cool. And then we remove at the beginning in order to get rid of that, so we don't run into an infinite loop. I remember that there was... I'm gonna have to Google this. Width of a binary tree. Oh, that's a LeetCode problem. That's a LeetCode problem, is it? Well, now I don't want to actually. Now I don't want to actually. Maximum width of a binary tree. Well, you know that there are n nodes in there, but we also need to check their two children to see if they have any. So I'm gonna say that it's linear. It still feels linear to me, but maybe I could be completely wrong on that. Oh gosh, I need to brush up on big O notation. And oh dear, what happened here? Return list. Oh, we never added it. Yeah, it might be nice to actually add our next layer to be traversed. That might help. Ooh, we ran into a TLE. Interesting. We can say, if next layer list is not... I believe that there is a is not empty function, but might as well just do not is empty. But yeah, we don't want to add empty lists, otherwise we will get TLE. Let's just toss in the rest of the example cases, and let's see where we end up. Okay, cool. Let's toss in the submit, and let's see where we end up. Watch as this is just way too much space. Okay, runtime of 26.52%, memory usage of 27.29%. Let me actually look at the details on that. Looks like we're a little bit slower than most submissions. What could we do to shave off additional time here if we really, really needed to? Hmm, hmm, hmm. We had to do this return list. Is there a guarantee that the values are... No. Because we still need the left and the right references, so we can't just do that. We... Hmm. Hmm. This is a good question. Traversal list add. And we can't just assume because one child has no children that the other will have no children. Let's see. Is there a way that we could do this BFS, or is there a way that we could do this traversal without BFS style, like a queue sort of thing? Now that would be interesting. I don't believe there is at least a simple way. I mean, maybe there's a way to recursively build it up. But like this is sort of just the straightforward way. I'm gonna give this a little bit more thought, but otherwise I think this is like, it's like fine. It's a little bit slow, but like it's not slow by I think that much. It's, let's see, 325 is looks like the 50th percentile ish versus 363, which isn't that bad. Similar situation here. But it looks like there's another solution that's even faster because there's another spike here, which leads me to believe that if there's a spike here with a shorter runtime and a shorter memory distribution, either it's some like crazy case or it's not so crazy and there is actually just a better way to do this than just the BFS style. I'm gonna give it some more thought because my mind is coming up empty right now. And I'll see if I can think of anything.